In this video, we're going to talk about increasing and decreasing functions. We're also going to talk about boundedness, lower bound, upper bound, and bounded, local and absolute extrema, symmetry, and we're also going to talk about asymptotes. So, another function concept that's easy to understand graphically is the property of being increasing, decreasing, or constant on an interval. We illustrate the concept with a few graphs. If we look at the one on the left, it's always increasing here. It's always moving up from left to right. As you look at the second graph, it is always going down from left to right. The third graph is always going to stay constant. It's neither moving up nor down. Now look at the fourth graph. It's kind of a combination of all these. It is going down, so it's decreasing from negative infinity to -2, including -2. It's constant from -2 to 2, and it'll be increasing from 2 to infinity. You got to remember, we're only looking at the x's. We're not looking at the y's here. Now, once again, the idea is easy to communicate graphically, but how can we identify these properties of functions algebraically? Let's look at exploration 1. Now, of the 3 tables of numerical data below, which would be modeled by a function that is increasing, decreasing, and constant? Well, if you look at the first one, y1, all the y values are the same. They are staying constant. So the first one will be C. If you look at the y values on y2, it goes 3, 1, 0, -2, -6, -12. That means it's going down. So that tells me it'll be B, decreasing. And you look at y3, it goes -5, -3, -1, 1, 4, and 10. All those values are increasing, so that would be A. Now if you look at 2, make a list of all the change in y1 values as you move down the list. As you move from y1, which equals A, to it should be y2 equals B, the change is B minus A. Do the same values for y2 and y3. Well, the change from -2 to -1 is 0. The change from -1 to 0 is 0. The change from 0 to 1 is 0. All of those are 0. Now, if you look at the change, the x moves from -2 to -1 at the next one, it goes down 2. From -1 to 0, it goes down 1. From 0 to 1, it goes down 2. From 1 to 3, it goes down 4. From 3 to 7, it goes down 6. Now you look at the next one. From -2 to 1, it goes up 2. From -1 to 0, it goes up 2. From 0 to 1, it goes up 2. From 1 to 3, it goes up 3. And from 3 to 7, it goes up 6. Now, in number 3, we're looking at the charts again from number 2. What is true about the quotients, change in y over change in x, for an increasing function? Well, our increasing function was our y3. So what's true? Well, the change in y over the change in x will be 2 over 1, which equals a positive 2. They're always going to be positive. They'll be positive for an increasing function. For a decreasing function, it will be negative. For a constant function, it will be 0. Where else have you seen the quotient change in y over change in x? This should remind you of the homework from 1.1. Well, we know slope is equal to the change in y over the change in x. Does this reinforce your answer in part 3? You bet it does. Think about it, positive slope is always increasing, negative slope is always decreasing. Now, your analysis of the quotients and change in y, change in x, and expiration should help you understand the following definition. A function f is increasing on an interval if, for any 2 points in the interval, a positive change in x results in a positive change in f of x. A function f is decreasing on an interval if, for any 2 points in the interval, a positive change in x results in a negative change in f of x. Then a function f is constant on an interval if, for any 2 points in the interval, a positive change in x results in a zero change in f of x. It should be fairly simple to figure out where these things are changing. So example 6, it says graph the function and identify intervals in which the function is increasing, decreasing, or constant. Well, let's graph it. Let's try that again. Now this is, where is it increasing, decreasing, or constant? Well, we know from our study that this point is -2. So everything's going to revolve around -2. Now this function is decreasing from -infinity to -2. This function will be increasing from -2 to infinity. It is not constant at all in this case. Now, if you look at B, looks a little bit different. Easy way to do this. Again, we could trace, but let's find where it can't be. From the bottom, we can factor the bottom to x plus 1, x minus 1. So I know x cannot equal 1 or -1. So I know this line here is -1. That line there will be +1. That will help us out on our intervals. Now, one thing that you guys might be a little concerned about is it does look constant on the outskirts. Nice, easy way, let's trace it. And you gotta watch the y value. You can see that the y value is constantly changing and getting smaller here, so therefore it is not constant. So, this function will be increasing from -infinity to -1. Also, it'll be increasing from -1 to 0. Now, these are not going to be in union because we're not talking about domain or answers and things like that. We're just seeing what intervals they're increasing on. So you just list them. It'll also be decreasing from 0 to +1, also 1 to infinity. Two different intervals that is increasing and decreasing. Now looking at C, put 0.5 times x plus 2 quantity squared minus 1. All right, if we look at this, we know this point here will be -2. That'll be its lowest point. Okay, that's its x value. So it's going to be, the point is actually going to be -2, -1. Now, it will be decreasing from here to here. So from -infinity to -2, it'll be decreasing. Then it'll be increasing from -2 to infinity. Now, you guys will probably say, you know, Mr. Gruick, it looks like it's constant right around -2, -1. Well, let's trace. As we look at this, I'm going to move down. It's going to keep going down. And then you'll notice it keeps going up. So you can see, as you trace, it's never going to be constant. It's constantly changing, if anything. So therefore, there is no constant part on this graph. The concept of boundedness is fairly simple to understand both graphically and algebraically. We'll move directly to the algebraic definition after motivating the concept with some typical graphs. Now, if we look at the first one on the left, it looks like it keeps going up and down infinitely. So therefore, this graph is not bounded above because it's going to keep going up, and it's not bounded below because they're going to keep going down. You look at the second graph. The graph is going to keep going up forever and ever and ever. But it's going to have a bottom. It's going to have a lowest point. It's going to have an absolute minimum in this case, which we'll get into in just a little bit. This one is not bounded above, but considered bounded below. In the third graph, it's basically just the almost reflection of the previous graph. It's going to keep going down forever and ever and ever, but it's not going to go up forever. So therefore, this graph would be considered bounded above. Now, if there's a top and a bottom that you can see like this, in the last graph, that would be considered bounded because it's bounded above and bounded below. Now, the definition for lower bound, upper bound, and bounded is a little bit tough to understand if you're not used to, if you're not used to the math language. Okay, so I'm going to basically go over it as we do this. Now, we can extend the definition to the idea of bounded on an interval by restricting the domain of consideration in each part of the definition to the interval we wish to consider. For example, the function y equals f of x. Let's graph that. 1 divided by x. As you can see, this is, as a whole, this graph would not be bounded. It's going to go up to positive infinity along the y-axis. It's going to go down to negative infinity along the y-axis. So this one is not considered bounded at all, unbounded. But if we restrict it from negative infinity to 0, this graph would be considered bounded above, because there is a boundary line above the graph. Now, if we restrict it to go to positive infinity, there's going to be a boundary line below the graph. Therefore, it is bounded below. So you have to be careful. You can see bounded on an interval. Now, example 7. Identify each of these functions as bounded below, above, or bounded on its domain. First graph. 3x squared minus 4. Now you can see that the graph's going to keep going up and up and up. Well, there's a boundary line below this graph, so therefore it'll be considered. This will be considered bounded below. Now you look at B. In this case here, I'm going to zoom in once just to get a better look at it. you can see it's not going to go up forever. It's not going to go down forever. So this one will be considered bounded because it's bounded above and bounded below. Now we put our last one in here, 2 to the x power, one of our power functions. You'll be able to see that there is a boundary line that the left part of the graph is following. So this here will be bounded below. Now again, I can change that last one. Say I go negative 2 to the x power. This one would be considered bounded above because the x-axis will be the boundary above the graph. Going along with boundedness is local and absolute extrema. Many graphs are characterized by peaks and valleys where they change from increasing to decreasing and vice versa. The extreme values of the function, or local extrema, can be characterized as either local maxima or local minima. The distinction can easily be seen graphically. The figure shows the graph with 3 local extrema, local maxima at points P, R, and Q. We'll see how to do these local and absolute extrema as we move on. Now, we've already mentioned that the best method for analyzing increasing and decreasing behavior involves calculus. Not surprisingly, the same is true for local extrema. We'll generally be satisfied in this course with approximating the local extrema using a graphing calculator, although sometimes an algebraic confirmation may be possible when we learn more about specific functions. Now, local maximum is a value that is greater than or equal to all range values in F on some open interval containing C. If it's the greatest, it'll be absolute. Same thing with the local minimum. It's going to be less than or equal to all ranges of values on some open interval containing C. If it's the lowest, it'll be considered the absolute minimum. Local extrema are also called relative extrema. We'll use those words interchangeably. Now, example 8. Use a graph to find all local maxima and minimum and the values of x where they occur. Give values to 2 decimal places. First things we have to do, we have to graph it. So if x is the fourth, minus 7x squared plus 6x. All right. Because it's an even function, and it's positive, we know it's going to open up. So what we have to do, though, we do have to switch our y mins instead of, say, minus 25 to see if it will fit. Okay, so therefore we can find our minimums. Our first minimum, we press second trace, go down to minimum. And we kind of do the same thing we did for finding zeros. I want to go left of where I want to find my minimum. I want to go right of where I want to find my minimum. Again, you see the 2 arrows and then the word guess. There's our first minimum at negative 2.06 for x value and a y value of negative 24.06. So we'll have, well, let's see, is it an absolute minimum or is it a relative minimum? Well, this case will be an absolute minimum because that's the lowest we'll have. So we'd say absolute minimum of 24.06 at, and that would be at negative 2.06. So there's your first absolute minimum. Now the second one, we want to find the relative maximum. maximum looks about there. Relative maximum of about 1.32, or local max. That's going to be about 1.32. And x is about 0.456. Then again, we'll have another minimum. My minimum happens right here. A minimum of negative 1.77. That's going to be at x equals about 1.6. And there you have it. There's your local maxes and local minimums. Moving on to B. We'll have 4 minus x plus x squared. Because it's an x squared, we know it's going to look like this. It's going to open positive x squared. It's going to open up. In this case, it'll be an absolute minimum. Absolute minimum of 3.75. And that's at x equals about 0.5. And there we have it. Now, if you're using absolute mins and maxes and relative mins or local mins and local maxes again and again, so this is one of the concepts you need to understand. If you don't understand them, you need to ask me right away.